So have you seen the PPT in the MS Team?
Yes, sir.
Yeah.
Yes, sir.
Okay. So I have updated that one. So maybe when Moodle will work, then we can go for the quiz. Okay. So you can maybe when you have free time, just you can go through the PPT. Okay. So today we will start about the theory of plasticity. So something is like I have already introduced in the previous module, but still I will put something new. Then also in the next class we will go about detail about some plasticity. So we'll talk about the theory of plasticity, basic introduction. Then also we'll talk about what are the, because when we are going for deformation or the plastic deformation, we have to understand the what are the basic mechanical property. Of course, we have studied little bit, but we will go in detail about the mechanical properties. And then also you have to understand the mechanism. How many times or how what kind of mechanism we have to become a failure, because we have to understand. So before failure, we have to go for the plastic deformation. And then also we have to understand the mechanical behavior phenomena. Then classification of deformation process almost we have covered in two ways. Okay, so one we have the according to forces or the loads we are applying. So here also I will show a little bit of with some schematic diagram. And then also we'll understand the plastic deformation. Actually, a small mechanism we will try to understand. And then also the common type of deformation. What are the basic, the general type of deformation what we are following. Okay. So before going to the in detail of the plastic deformation, so you have to understand the theory of plasticity deals with the behavior of materials at a strain where the Hooke's law is no longer valid. Okay, so these are the behavior of the materials, the strain rate or the stress. These are already we have covered, and also based on the strain rate, we have done some numerical also. So if you remember your Hooke's law, maybe you have studied somewhere. So F equal to minus Kx, where F equal to the force and x is the extension length. How much length actually, when for example if you have taken a spring, so when you are stretching, how much length you are increasing with respect to the initial one. And k is the constant of proportionality. So these are the Hooke's law actually what you have studied in the past. And when the Hooke's law is no longer valid, then only we are understanding this is the plasticity behavior or the the strain that you are considering there. So a number of aspects of plastic deformation make the mathematical formulation of the theory of plasticity more difficult than the description of the behavior of an elastic solid. So if you remember, I told one time the FEM analysis or maybe any kind of the simulation analysis, because whenever you are doing some experiment, maybe in the ancient time or maybe in the old time, we didn't have that kind of simulation or that kind of software. So every time we have to go for the basic experiment. Okay, but if the plastic deformation, we also I told maybe in laboratory scale, sometimes it will be much more difficult because you have to go for a large metal piece. And then also you have to deform that one, because in laboratory scale it will be much more difficult because you cannot find that kind of scope there. So to going or to overcome that one, you have to go for any kind of simulation or maybe the mathematical modeling or maybe something. So that one will be much more a little a bit of clarity they will give you. For example, the plastic deformation is not a reversible process like elastic deformation. Okay, for example, if you are talking about the elastic deformation, after removing your load, then again it will come back. But whereas when we are talking about the plastic deformation, after removing the load, it cannot again go back. So you will find another shape or another geometry. And the elastic deformation depends only on the initial and final state of stress and strain. Okay, so if you want to compare the elastic deformation and the plastic deformation, whereas in elastic deformation, this depends only the initial and final state of stress and strain, while the plastic deformation depends on the loading path. Okay, so if you remember, the compression, the tension, direct compression, direct indirect compression, these are already we have studied. Then tension, then torsion, these are already we have covered. So this depends upon the loading path, in which way actually you are giving the force or you are giving the load there. And the theory of plasticity is concerned with a number of different types of problems. So any kind of, I'm just talking about here the plasticity or the plastic deformation, but wherever if you go to any kind of mechanism or any kind of equipment or any kind of process, you will find somewhere some problems or some obstacles there. You cannot tell that this process is the best one. We have no limitation or we have no disadvantage. All the things are we are getting the advantage. So from the viewpoint of design, the plasticity is concerned with predicting the maximum load. Okay, so that means you are predicting the maximum load which can be applied to the body without causing accessibility. Okay, because if you are going to excessive building, so that is not required for plastic deformation. So that means we have to limit within the yielding area or within the yielding zone. And the yield criteria must be expressed in terms of stress in such a way that it is valid for all state of stress. And the designer is also concerned with plastic deformation in problems where the body is purposely stressed beyond the yield stress. Because sometimes when we are doing research, like in the last class also, I told about the metallurgical aspect, because whenever we are doing something, we have to overcome. For example, if you remember, I told if you want to go to with the strain path A, in the last schematic diagram, so you do not think that only this strain path A is possible. So what you have the alternative? You have the alternative, if I can go to the strain path B, then whether it is possible or not. And the similar way also, what we do if we have the material A and material B. So if you are doing the best thing for material A, but what is the alternative way so that I can change to material B, so that also it will be success. So you cannot tell that only we have to go for only before the yield stress, but after the yield stress or beyond the yield stress also, whether this is possible or what kind of study I can do, that also you can do, right? Is it clear? Yeah.
Yes, sir.
Yes, sir.
Okay. Then the consideration of a small plastic strain allows economies in building construction through the use of the theory of limit design. Because sometimes also you are asking, sir, if we are doing this kind of process or this kind of technique, whether this is expensive, the cost factor is coming. So here I mentioned these economies. Okay, so whether this is feasible for me or not. And the analysis of the large plastic strain is required in the mathematical treatment of the plastic forming of the metals. Because whenever you are going to any mathematical modeling or the simulation, because what you are doing, like some kind of ANSYS or maybe some kind of other software you're using, why you are using? Because you are predicting. Because I remember some of the students, you were telling that, sir, I can apply the load also or maybe weight also. A lot of parameters are there. You cannot stick on only 2 or 3 parameters. Okay, maybe I asked about maybe why you are choosing this course. Maybe somebody you told that maybe whatever we learned the simulation we can implement there. Of course, this is possible, but that simulation is because this is expensive. Let's say this is 5 lakh. So that doesn't mean that only 2 parameter or 3 parameter you are only thinking. Lot of parameters are there. That's why it is expensive. And based on this parameter, then you have to predict something. So that is the basic reason of the simulation, right? It is very difficult to describe in a rigorous analytical way the behavior of the metal under these conditions. So, sometimes I told you, or maybe you asked me, sir, how we will know this one? Of course, this is very difficult because you cannot, for example, I'm, let's say, fresher. So I cannot tell that what kind of material they are using or maybe what kind of behavior it is showing, or maybe it can show. But when, if you will go to any company, if you will go to any company, if you will meet very senior scientist or maybe the managers, general manager, somebody, so they will see the material or they will predict something, and they can tell. For example, if you will go to the doctor, let's say the fresh doctor, maybe age is, let's say, 30-year-old, maybe 25-year, but if you go to a 50-year-old or 55-year-old, he will just see and he will tell that what kind of disease or what kind of problem we have, right? So therefore, a certain simplifying assumptions are usually necessary to obtain a tractable mathematical solution. So to find out a good solution, so we cannot tell that I do not know, I do not have any option to do. We have to find out the solution. We have to tell. So why we are going for simulation? Because to find out some sort of solution there, so that we have to go for simulation. Then if we predict something, then based on that we have to go for the analytical, or we have to go for the experimental purpose. Okay. And another aspect of plasticity is concerned with acquiring a better understanding of the mechanism of the plastic deformation. Okay, so one more aspect also when we are talking about the plasticity, the mechanism. Every time, because sometimes the students, they are coming and they are telling, sir, this is the raw material or this is our goal. So only we will put a furnace or maybe we will do something like machining or maybe rolling or forging. So we are getting that one. That is okay, that you have to do. But at the same time, if somebody will tell that, because we are engineer, so somebody will tell that in which way actually it formed one to another. So we have to go for example, now I'm talking about the deformation. So you have to understand what kind of mechanism. Maybe today I will just show some things like, or maybe I do not know whether I prepared that one. Maybe in the next class I will talk about the sleep, twinning, little bit of. So that's why I told what are the possibility to go for fracture, because only we had after plastic deformation we have to go for fracture. But what kind of the process we have to go to the fracture? Then the effect of metallurgical variables, for example, the crystal structure and the lattice imperfection on the deformation behavior are of a chief concern, because whenever we have to go for the deformation, you have to see the crystal imperfection or the crystal structure, and also you have to understand the mechanism or the microstructure or the transformation, like phase transformation, one phase to another, then next phase to the, another phase. So that's why we have talked in the previous class the recovery, recrystallization, grain growth. Okay, is it clear about the plastic deformation? Again, the basic background. Okay. Yeah.
Yes, sir.
Okay. So then when we are going to the plastic deformation, then again we have to study the what are the basic mechanical properties of the metals. Okay, because what are the properties we are going to, or we are going through this, so we have to understand in that aspect. And the mechanical property of the material reflects the relationship between its response or deformation to an applied load or force. Okay, so that means how much force you are applying, and that one will make a response. For example, if I'll give one more example, for example, we have some disease. Maybe you had this one. So doctor will give some medicine or maybe some injection or maybe something. So the doctor normally they will tell the the person or the the patient whether his body is responding or not. Right? You had this statement from the doctor normally. So here also we have to understand that whether we are applying a load or maybe force to that metal, whether this is responding to deformation or not. If this is not deforming, so that means this material is not responding. So that also we have, this is the beginning aspect. Then other properties are strength, hardness, ductility, and stiffness. These are also we have to understand. Maybe one slide also I put in the last. Okay, after finishing the fracture and everything. And these properties are ascertained by performing carefully designed laboratory experiment that replicate as nearly as possible the service condition. So you have to go for, that's why I told maybe in the several times. So initially we have to think our idea whether this is feasible or not. Then based on this we have to make a design, make a in design in the sense do not think about the building design we are making. Design means, for example, whatever the experiment we will do, let's say step 1, step 2, step 3. So this is my design, I prepared accordingly, or I will prepare accordingly. Okay, then you have to go for the laboratory scale. Laboratory you have to make the test whether this is working in a proper way or not, right? The moment you will go for laboratory scale, then you have to go for the pilot scale. Pilot means a little bigger amount. Let's say you are making 2 gram, 5 gram, or maybe 6 gram. Then you have to go for maybe 30 kg, or maybe 40 kg or 50 kg, let's say. Then after again success, because you will find a different here. Here 5 gram, here you are taking 30 kg. Okay, so you will find a lot of difference there. Then when you will success, then again you have to go for the industrial scale or the big large scale. In the similar way, what the vaccine actually they are doing. So initially they are doing the laboratory scale. For example, after finishing, then again you are going to the little bigger scale. Then when bigger scale, then again they are making trial for maybe 1 or 2% or maybe 10%. Then again they are making 100%. Then again they are trying for 1 lakh people. They are doing like this. So the factors to be considered include the nature of the applied load. Okay, what kind of load you are giving, because what should be the nature of the load. Then its duration, how long, because that is also is applicable in heat treatment also. If you remember, how much time you are holding. Here also how much time the load you are applying there, as well as the environmental condition. This environmental condition also you have to think. Okay, because sometimes if you remember the vaccine, initially they told that you have to put in minus 20 degrees C. Okay, but if you will go to the Russia or maybe other side, their atmosphere is different, so they do not need to worry about the refrigerator who had to store that one. But in our case, our country is hot. For example, here you can see now in January, the humidity is very high. But if you go to now some other country like Russia or maybe some European country, and there is snow now. Okay, so depending upon the environmental condition, also you have to think. It is possible for the load to be tensile, compressive, or shear, and its magnitude may be constant with time, or it may fluctuate continuously. So you have to think about whether the load is tensile, compressive, and also its magnitude. The number you have to tell that this is the accurate number. For example, this is constant, or maybe you can vary, or maybe it is fluctuating. And also the application time, how long. Okay, and the service temperature. The temperature is also one more factor. We have already discussed about the temperature also, right? Is it clear? Yeah.
Yes, sir.
Okay.
Yes, sir.
So yeah, so this slide also you have to understand that here I mentioned what are the basic mechanism to become or to find out the failure. So if failure is considered as a deterioration in a desired performance, which could involve changes in property and or shape, because we are going towards the deformation, and we are going to find out the different property, different microstructure, at the same time also different geometry, the shape and size. So then failure can occur by many mechanisms. Okay, so what are the basic mechanism we have? So we have the elastic deformation. Also, you are finding their deformation. The failure. And then also you have the plastic deformation. So these are some of the process. Maybe if I will check if we have time, probably I can go maybe 1 or 2 slide of the twinning or slip, how actually we are making, etc. Apart from this also we can find. Then also the fracture, and then also the fatigue, and then creep. I think these are already probably small information you have already got from other courses. But also I mentioned small definition how actually we are getting. And then also one more thing, we have the microstructural changes. For example, the twinning or maybe the phase transformation, grain growth, particle coarsening. These are also small part we have already covered. Then apart from this, left hand side, so this side is also possible, because you cannot tell that only fracture or creep only due to this mechanism we are getting to failure. But apart from this also we have, for example, the chemical or electrochemical degradation. Okay, so if you remember or if you know the corrosion or maybe the oxidation, also you can find the failure. Then these are the physical degradation. We have the wear and the erosion. Okay, so this one probably you remember I told in the machining part, maybe a small 112 slide we have covered this one. So these are the basic mechanism we have when the material actually they are going to a failure, or maybe they can fail, right? Yeah. So here I mentioned the type of mechanical behavior phenomena. Okay, so when we are going towards the classification, how the mechanical behavior we are going towards, what are the basic mechanical behavior we have. So one is elasticity, plasticity, the fracture, fatigue, and creep. Okay, what we have mentioned in the previous slide in the left hand side. Okay, so that mod parts, and other parts are a little different, not the typical one, but also apart from this mechanical behavior, also you are finding some other, the corrosion, oxidation, or maybe the physical one. So here you can see I just put one small example for you. Elasticity, so that means you are recoverable deformation, whatever the deformation you are getting, but that deformation also you can recover that one. For example, you are taking a spring. Okay, so original length you have, so you are after releasing also you can gain that old position. Then plasticity is the permanent deformation. So that means if you have a steel rod or any kind of metallic rod you have, so you are just bending. So that means after bending, you cannot regain that one, or you cannot go back. Then fracture is propagation of cracks in a material. Okay, so that means propagation means it will propagate initially, or it will start initially. Then again, it will increase the size. For example, if you can take this sheet here, maybe for example, this aluminum foil or something. So you will find a small crack here. Okay, in the left hand side, you can see small tear or maybe small crack. So after that, when it will propagate or when it will increase, you can see it is increased. Then finally, you have to go for a bigger one. Okay, so that means the crack propagation in the material. Then fatigue is oscillatory loading. So that means your load whenever you are making. So these are actually fluctuating. This is not constant, in a oscillation manner. Okay, so maybe it is going, then again it is fluctuating. For example, if you will see when we are making the copper sulfate, the dissolution, or maybe the recovery of copper from the copper sulfate. So what we are doing, the current or maybe the voltage one, you have to make it fixed. For example, if voltage you are making it fixed at let's say 1 volt, the current will fluctuate. The current will not be constant. Maybe after some time it will constant. Because when everything recovery will be finished, but in the meantime it will fluctuate, because you cannot tell that all are in a similar way. Okay, so it will fluctuate. Then another one, we have the creep. So elongation at constant load or constant stress at high temperature. Okay, so that means you are giving a constant load there, or maybe the constant stress, because the or with respect to the unit area or the surface area, but at a high temperature. Okay, so these are the mechanical behavior you are getting with plasticity, elasticity, and then fatigue, then fracture, then creep. Right? Is it clear?
Yes, sir.
Yeah. Okay. Yeah. So then one more, this slide I have not talked in detail actually in the previous module. So whenever we are talking about the deformation process, so again in deformation you can make it elastic and plastic. So what this is recoverable and this is permanent. Again, the elastic can be classified in two ways. One is instantaneous and one is time dependent. Again, if you go to the time dependent, because instantaneous means suddenly, like in instantly, okay, immediately in there you can find. Time dependent with respect to the time. So again, you can classify one is unelasticity and one is viscoelasticity. And similarly, if you go to the plastic deformation, you will again find instantaneous and time dependent. And the time dependent, again, you will go for the viscoplasticity. So I put just one line for these three, because these are all the general terminology we have. But the three terminology I have added here, one is unelasticity and viscoelasticity in case of elasticity or the recoverable one. But whereas if you have the viscoplasticity, this is in the plastic deformation. So unelasticity is a recoverable deformation under load, okay, results from internal friction and contributes to internal heating. So that means if you have some internal friction, maybe I will show one more slide today. So only we are talking about the the load and everything. But apart from this, also you have some friction. Okay. And I will show one good photo. Maybe normally, we are not recalling that kind of day-to-day basis what we are doing. But I put one slide. Maybe you will find interesting that. And viscoelasticity, this is, for example, the metals. For example, I put here metals at very high temperature. Okay, so that means this is a time dependent, okay, and recoverable higher strengths with nonlinear behavior. And the third one, we have the viscoplasticity. So I put one example here, like metals, any kind of metals, okay, because after plastic deformation, so that means you cannot recover that one. Okay, is it clear?
Yes, sir.
Okay. Then we have, yeah. So then the plastic deformation, only we understand the basic, the microstructure and everything. But if you will go for in the atomic state, okay, in the atomic state, how actually it can looks. Okay, maybe if you will go in detail, or maybe if you can assume or predict maybe how actually it can be possible inside atoms. Because just only we thought that, okay, these two rolls are there, one big the sample or maybe the plate I'm just pushing there, then two loads, it is rotating, rotating, then only there is a small gap, so this is passing, so we are finding another one. But if you will see the atomic level, how it can be possible. So from an atomic perspective, plastic deformation, and one more thing just I will tell in the previous slide, the plastic deformation in the broadest, because if after the initially we are applying the forces or the load, but after the plastic deformation, then the external constant, whatever the external constant you have, the forces or the displacement, these are all you have to remove, because there is nothing. This is now equilibrium, or this is now stable. From an atomic perspective, plastic deformation corresponds to the breaking of bonds with original atom neighbors and then reforming bonds. Okay, if you remember that microstructure I have shown you. So initially the atoms you have to, the stretch one or the bigger one atoms you had, then you have to detach that one or you have to deform that one. Then from that deformation, you have to find some new grains or new atoms, small particles, if you remember. Then that atoms again it will go, or again it will increase there. Then finally you have to go for the grain growth. Okay. So here for most metallic material, elastic deformation persists only to strengths of about 0.005. So if you'll see the schematic diagram here, the plastic deformation, so initial atoms you have here. Okay, so this is the initial one. So the moment you are giving some load here, or maybe you are stretching, because here you can see in the top, this is, for example, this is fixed one. Okay, so there is a roof, let's say. Okay, so this is fixed. So you are giving a force here, okay, in the bottom. The moment you are giving a force here, so that means all the atoms, initial atoms you had, so how you can change here? Okay, so that means we are applying a load here. We are stretching from the bottom. So bond stretch and the planes also this here. So that means these atoms will be enlarged. It will increase again. And the moment if you will find this one is the the borderline or maybe the benchmark here, the dotted line in the bottom. So you will find the elastic and plastic zone here. Because after a recovery, I'm talking about the atoms only. So after recovery or maybe after removing the load, so maybe you will find this much of distance from the dotted line to this dotted line. So you will find a little bit of decrease. So that means the third one you can see this is the unload. Okay, so whatever the distance you had from here to here, because this was elastic plus plastic, both these ones were there. But whenever you are removing the load, this F you are removing now, so you will find this much of zone here, and that zone you cannot recover. Okay, and the moment you cannot recover, that zone is known as the plastic zone. If it is totally recovered, then also you will find this is elastic also. Okay, because you have elastic and plastic. So as the material is deformed beyond this point, the stress is no longer proportional to strength, the Hooke's law. So that is, I told in the beginning of the slide, when you have or when the Hooke's law is not valid, then only you have to go for the plastic deformation, right? Okay, this is the basic mechanism. Okay. Yeah. So one more slide also, I put the schematic of stress strain diagram showing the plastic deformation. Okay, whatever I told these three, the atomic structure. So again, you put in other way. Okay, for example, this is initially. So you have the elastic in nature. Okay, so that means if you will give a load here, okay, this load, if you are giving, so that means you have to give up to here the yield stress. Then again you are getting, you are stretching, or that means you are giving a load there. So the moment you are giving the load, you will find this kind of atomic structure. That means this is elastic plus plastic region. And the moment you are taking the load, or maybe you are removing the load, so you will find this line. Okay, so that means this is on load. And the moment you are removing the load, you will find this kind of structure. Okay, so then it is known as the plastic zone, or maybe the plastic region, right? And this is known as the EP, and from this to this distance is known as the plastic strain. Okay, if you will take the graph of engineering stress and strain, right? Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay. So one more thing. Yeah. So then some of the properties I just told, probably you know this one, all the mechanical properties, what are the property actually we have available. For example, the tensile property. So what is the yielding? These are already I know, but still I put, maybe if somebody forgot from your materials and technology, or maybe strength of material, just you can have a look. Yielding is the beginning of the plastic deformation. Okay, and the proportional limit here, this is proportional limit. So the point at which there is a deviation from the straight line, the elastic regime. Okay, so whenever you have the straight line here, when it is finding some deviation from there, so this is known as the proportional limit. And the yield strength. Okay, so this one is yield strength, the stress at which the noticeable plastic deformation has occurred. Okay, for example, we are talking about the average one. Sometimes, we are taking 3 experiment or maybe 3 readings, then we can take the average. Okay, so what we are telling, this is stress at which noticeable plastic deformation has occurred. Okay, so this is basically known as the tensile property. Maybe you can just have a look when you have free time. Then one more thing, the yield strength actually, when we are comparing, because only we are talking about now here, for example, the metal. Okay, but apart from metal also, we have other materials. For example, if you will see the yield strength here in the y-axis, and the x-axis, we have the different kind of material. For example, the metals and alloy, or maybe graphite, or maybe polymers or composite fibers. So if you will see how the yield strength you are comparing with other. Okay, for example, steel, you can see higher yield strength. Similarly, for example, titanium or tungsten, copper, molybdenum, you can find like in this way. And whereas if you go for the polymer, you can find the yield strength is here. Okay, how much you can, for example, this is, let's say, PVC. Okay, normally we are using PVC. This is around 40 megapascal. But whereas if you compare with the PVC for steel, you can see here around how much, maybe 1500 or maybe 1700 you have this steel. Okay, so these are the basic comparison. Maybe when you have if you are interested with some different materials, why we are giving the comparison, because these are some of the researchers, they have already established this one. So for us, this is very easy, that when we are going for any kind of experiment or so choosing a material, at least we can choose from here, because this is already people they have done. So we do not need to do again. If you want to cross check, you can do. That is not unhard. Okay. And then next we have the tensile strength. So the tensile strength also, if you have the graph of engineering stress and strain, so you can find this is the tensile stress here. Okay, so the tensile strength is the stress at the maximum on the engineering stress strain curve. Okay, so whatever you will get the maximum one, apart from it, beyond this maximum, again it will decrease. So you will find the fracture here. So I put some schematic diagram here also, how the necking is happening. You can see how the necking is happening, then how it is going towards the fracture. Okay, so in case of the metals, in case of the ceramic, in case of polymer, the property is different, because normally we are telling about when we are talking about the fracture or the necking. So we are talking about metals every time. For example, the metals, this is the point when noticeable necks start. Okay, we are considering metal, but in other material, if you will take, we will not tell necking. For example, in case of ceramic, we are calling crack propagation. Okay, so that means your crack will increase, or it will propagate. In case of polymer, the polymer backbone ends are aligned and about to break at this point. Okay, so you are not calling necking there, because metal when necking, if you will go to your UTM machine, if you have done in your first year or maybe somewhere, so maybe you will find a necking, because normally we are going for metal, but we are never doing the ceramic or the polymer. Maybe when you will do, probably you can tell to your faculty that let's try for a ceramic and polymer. Okay, so you will find different things there. Then also this is one more comparison, the tensile strength with different metals and materials. So this is metal and alloy, this is graphite, this is polymer, and this is also composite fiber. Okay, so if you remember this kind of slide also I have shown in composite materials when we launched that one. Okay, so you can, if you are doing some work with some different kind of metals, so also the tensile strength, if you are considering, also you can correlate with, for example, steel and the the fiber reinforced composite also. You can compare what should be the tensile strength. Okay. Then next we have the ductility and the percent of elongation. So these are also you have known ductility may be expressed quantitatively as either percent elongation or the percent reduction. So the formula is the final length minus the initial divided by the initial length into 100. Okay, so if you take the schematic diagram of the change of material, so if this material is initially the area is A0 and you are finding now AF and the length also it was let's say L0, and after deformation you are finding LF. So you can find the percent of reduction area also that we have done. Based on this also we have done some numerical A0 minus F by A0 into 100. Okay. Yeah. And then next we have the toughness. So what is toughness? Actually the energy required to break a unit volume of material. Okay, so if you will see the engineering tensile stress and the engineering tensile strain, so if you have the material, because whenever we are talking about the ceramics or the metals and the polymers, so ceramics normally they give small toughness. Okay, so they give small toughness and their graph will be different. Okay, so that's why it is better to put in one graph. If you are checking with 3 or 4 materials, so if you put in one graph, it will be much more easier to make a comparison. But if you put separately, maybe it will be difficult, how to make a comparison. So in case of metal, you have the large toughness. Okay, but whereas if you have the polymers or the composite kind of material, so you have very small toughness. Okay. Yeah, so one more we have the resilience. So the resilience also, if you will see the schematic diagram here, you have the stress and strain. So the resilience is the capacity of a material to absorb energy when it is deformed. Okay, so if you remember our the deformation, the schematic diagram I have shown, you have the lubrication, you have the friction, then you have the energy also. So the moment you have the energy, okay, how much energy is absorbed by the deformed metal? So that is known as the resilience. Okay, the capacity. Then also one more thing, modulus of resilience is the strain energy per unit volume. Okay, so how much of strain energy you are getting or you are finding with respect to per 1 unit, okay, per or 1 unit volume. So this is known as the modulus of resilience, right? Is it clear up to now?
Yes, sir.
Yes, okay, sir. So these are already but just only I'm making some recap. Then also hardness also you have done in strength of material, I think. So resistance to permanently indenting the surface. Okay. For example, if you have the large hardness, that means the resistance to plastic deformation or maybe better wear property. Okay. So there are so many types of tests we have, Brinell, Vickers, and Knoop, or maybe the Rockwell. Okay. So you have the indenter also. Different indenter normally we are using for different tests. Okay. And different formula also we are using. Okay. So I think you have already done with some application, with some calculation or some numerical also you have done, I think, in some. Okay, so we are not going detail because these are the properties. Just I want to recap for you, because when you do not think that only strength of material we are studying there, but whenever you are also going towards the metal forming or the plastic deformation, also at the same time also this is correlating. So all these subjects are almost correlating. Okay, so you have to correlate accordingly. Then the stress and strain also, what is true stress, what is true strain. Then also what are the basic the relationship with engineering stress and engineering strain. Then also this graph also I have already discussed about stress and strain. Okay, so here is you are finding the fracture and what is the true stress strain diagram and what is the engineering stress strain diagram. Okay, so these are already we have discussed. Then yeah, so this slide is important now. So you have to understand what are the common type of deformation. Okay, so basically we have the tension and compression. Then we have but I have added one more thing is torsion here. Okay, so maybe with one schematic diagram you can just go, and this is the tension you have because if you have a metal piece or maybe you have a material here, so you are stretching both this side, so you will find some elongation is there. Okay, or some expansion is there. Similarly, if you have the compression, so that means you are pressing, okay, from both this side. And if you have bending, so that means if you have a metal piece there on the top, So that means you are making some bending moment in the both the side, so that you are getting the material bending. Okay. And we have the shear actually. So when you have shear means, so that means you are giving a force from the top or in the top side and also in the bottom side. So that means this is going towards slip. Okay. So on the top and bottom. And the moment another one we have torsion actually. So torsion is like, squeezing. Okay. For example, after the wet cloth. Okay. So normally we are squeezing to remove the water. So in the similar way, so that means you have to squeeze. Okay, in the both way you have to squeeze, so that this material will become like in a torsion kind of structure. Okay, so if you'll see the another schematic diagram I put here, at a more fundamental material level, there are only two types of deformation. One is tension and compression, or usually tension and compression during bending. So you can find this kind of the bond angle actually you are changing here. Okay. So for example, you have the metal piece here. So now the moment you are giving the shear, let's say, so your the bonding will will change, and the metal piece also it will shift to from one place to another, or maybe from one side to another. And if you have the tension actually, so if you are stretching the both the sides, so again your metal piece will it will shift, and also your the bonding also it will move, or it will also change, because the moment your atoms also it will change, so your all the structure also it will change. Okay. Yeah. So next one we have what can happen. So one question actually I have added here: what can happen to a material body or solid material on the application of external loads, forces or constants? So whenever you are giving some external force, so what will happen? So for example, you have the contraction or dilation. For example, one volume change. Okay, so one is volume change initially. So if you have this kind of material, so maybe it can be squeezer if you are giving compression. But if you are making tension, maybe it can be a change like this, bigger shape, like volume change. The next one we have the shape change. Okay, so if you are giving this here, so you will find this one. Okay, in the previous slide I have mentioned. Then the next one we have the rigid body rotation. Okay, so if you want to make some rotation or the orientation change, orientation of the crystal, if it will change, then again you can find this kind of structure. Okay, so one more thing, I put one example of this showing how the parts of a single body may have different responses to loading, because sometimes we are talking about only we are if we have a cantilever, if you remember, somebody was asking me about this is like a cutting, the shear, one type cantilever, and then other side if your punch you are pressing, so it will cut, because if you have a big billet actually, if you want to make it smaller billet, you have to cut it. Okay, so that's why we are going for shearing. Here also if you have two support here, okay, two support here, and you are pressing from the top or in the middle, and this is the metal piece or maybe the plate. So how you are giving? So that means you are giving two force here actually, because there are two force. It will oppose there. The moment you are adding the force on the top, so in the two the point, you will find some opposite reaction there. Okay. So finally, you have to get this kind of structure. And how you will find this kind of structure? One is here and here. But apart from this, also you will find one kind of the moment also from here. So this region outside the support undergoes a rigid body rotation and is not stress. Okay, so initially you will find here something. Okay, so whatever I put here, you will find some opposite reaction here. But at the same time also you will find some reaction here. Okay, outside the support or outside the support region. Right? Is it clear? Yeah.
Yes, sir.
Okay, so I think one more slide, only this last slide, then we can stop. Yeah, so this slide, sometimes we are not taking care, or we are not considering much in this kind of case. For example, if you have a metal piece or maybe material piece here. Okay, so now you want to give force on the top here. So the moment you will find the force, or you will give the force here, the metal is not moving. The metal you are fixing here, because this is, for example, a elastic or maybe like some kind of rubber here. So this will move like this because you are pressing here. So that means this is moving on the top, but bottom is fixed here. So if you will see the metallic schematic diagram here, you have the initial material like this. Then the moment you are giving the force on the top here, so you will find opposite reaction here in the bottom. Okay, because it will not move. The moment also it will move, so you will not find any opposite reaction. So that means it is fixed here. So the moment you are giving a force here on the top, so you are finding opposite reaction here. If you are giving a T here, you are getting minus T due to the friction. And the moment you are getting the friction here, minus T, so you are finding some opposite reaction here also. Okay, this zone, left hand side zone. So the moment you are finding opposite reaction here, then also at the same time to make it equilibrium, you will find different reaction here in the opposite side. Okay, for example, you are getting R here, let's say, so you are getting minus R here. Okay, so one more thing we have if you have the shear, this is simple shear and the pure shear, the angle you are talking about, maybe you have studied in the orientation or the crystal structure in the maybe I do not know if you have studied. So about the angle also we are considering, what is the gamma for and for the simple shear how much. Okay, you are also considering that one. That is also important for you. You have to study. Okay, fine. Yeah.
Yes, sir.
Any question up to now?
No, sir.
Okay, so we are going a little, maybe you have to little understand the detailed mechanism, because sometimes in the upper side we are just going, this is happening or this is happening. But if you want to study the mechanism in detail, so of course you have to go in deeply, because for example, maybe we are now doing small numericals. So maybe sometimes we are assuming this thing, that thing. But if you are not getting in the proper way, then you have to assume something. The moment you will assume, and then probably it will be much more better, like thermodynamics, what you are doing. Sometimes you cannot predict, so you will assume. Let's in mathematics also, if you remember your arithmetic when you were doing in the 6th, 7th standard. So if you are not doing, if this is very difficult, then you are assuming this is x. Like similarly here also we have to assume something, then only we can do something.